Hello! Welcome to the second video of the series, How Neural Networks Learn. We recall the first video that we discussed the mechanics of learning, we covered weights and biases of neurons, we digged input and output shapes. More specifically, we transformed an input vector by multiplying a weight matrix and added a bias term. That's great. We made a linear transformation. For many problems, we need nonlinearity too, and we already solved that. The set of nonlinear transformations are called activation functions. Activation functions contribute in two ways. First way is NNs can approximate nonlinear functions by the help of activation functions. Second way is also a way that linear functions cannot help. We can squash the output range into a range that we want, such as range 0 to 1, minus 1 to 1, or plus 1 to infinity. Here is important because we should choose an activation function that suits the output we want to produce. If we want to make a classification task, we need class probabilities. Hence, range 0, 1 is suitable, but if we want to make a regression, we need a wider output space. One point is that whatever function you use in an architecture, they should be smooth enough. They should be differentiable so that gradient calculation in backward pass goes smoothly. We will go over popular activation functions. Here is the list. We start with ReLU rectified linear function. Function itself is a simple one indeed. Here is this one. If the input is less than 0, output is 0. Otherwise, the output is input itself. So it's a combo of the zero function and linear function. If we look at the figure again, at this region, derivative of this function is 0, and at this region, slope is just 1. This func looks harmless, though notice if the input goes to this region, a zero derivative will come, and by chain rule, the result of backpropagation will be just 0, so no updates will happen to the weights and biases. That's bad, then your NN either won't learn or learn slow. There is a remedy to this situation by giving a tiny slope to this region, and that activation is called a leaky ReLU. Let's play a bit. Here is the input and dense layer from the previous video. I will just run it through the dense layer, the input. Okay, it looks like this. So each row came 0. Most probably there is a minus term in the weights that made everything negative, so everything is 0. Let's try this one. I flip the signs. Okay, these ones are positive, at least for this one. I think weights are just negative when multiplied, produce something positive, so they came. And this one fall to the 0 region. One more example. Okay, this is all positive because I flipped the sign here also. Let's transform another one. That is, shape is a bit different. Now I will transform an input of batch 1 and dimension 3. Here it is, and I want to output of shape 2. Hop. Here it is. First one is a positive. Second term is just 0. And one more. This time I will do 2 batches of in dimension 3. Hop. Okay. Here it is. Great. As you see, this function generates either 0, no negative values, or just some positive values. Here in this region, it can be 0, small value, such as 0.1, or something a bit bigger, or something much more, such as 4 or 3. Next function is sigmoid. What can I say? It is sigmoid, smooth, differentiable, and squashy. Sigmoid function's graph is a S-shaped curve, like this. Beyond minus 10 and plus 10, it's spread flat. Action happens in this region. Sigmoid is denoted by sigma usually, like this. This is the function. So some properties are just domain is minus infinity to infinity as you see on the graph, and the range is squashed to 0 and 1. Sigma of 0 is just 0.5, and this is a monotonically increasing function. Also, this function is also continuous and differentiable everywhere. First thing we should know is sigmoid is a squashing function. This is important. It squashes positive and negative real numbers into the range 0 to 1. Hence, even if the input is a very large positive number somewhere here, or a very small negative number somewhere here, still output is between 0 and 1. So what makes sigmoid a good activation function? First of all, it's smooth, differentiable, and monotonically increasing. Second of all, it's nonlinear, sometimes we need it badly. But most important thing is that it generates an output between 0 and 1. Hence, if we want to output some probabilities, it's a great choice. Let's shoot some examples. Here is the example. Again, dimension is 3, it's one batch. I want to output one value between 0 and 1. Okay, I get this one. Let's try this. This is 0.5. Now I will transform a batch of 3 inputs. Hoppa. Here it is. Everything is between 0 and 1. Next one is tanh or tanh. Tanh is a shifted and stretch version of the sigmoid. Here is the formula first, and here is the graph. It's an S shape again. The output range is -1 to 1 and presents a similar behavior with the sigmoid function. Let's shoot some examples again. It's the same. Input, hop, and then hop. Okay, I was able to get a -1. And this one, again -1. Maybe inputs are too big. Okay, this is, I flipped the sign, I changed the numbers. So I get a 0.99 somewhere here. And then let me try this one. Okay, now I get something, more smaller side. I think these numbers were just too big. They saturated, come near this region. But here it is. Here are the results. Now comes a small discussion. We want two things from an activation function: differentiability and nonlinearity. Nonlinearity is important. Otherwise, the repeated applications of this linear transformation, Vx plus b, results in a linear transformation. Differentiability is important for computing gradients of backward paths, if you recall from the first video. Point discontinuities, such as in this one in ReLU, is fine because it's just one point. We have a look at the graphs again. They have at least one sensitive range where non-trivial changes correspond to a non-trivial change to the output. For example, if the input jumps from here to here, the output goes from 0 to a positive value. Many of them have a saturated range, where the changes to the input results in little or no change to the output. Just like here, these areas are just 0. If you go from here to here, result is still 0. Or if you take sigmoid, if you are here, you go from here to here, result is still very near to 1. If we go back to the propagation, the errors will propagate more proactively when the inputs are in the response range, while the error will not really affect the neurons that are already saturated. Saturated area has derivative really near 0, hence if you put this derivative into the back propagation computations, 0 back propagates and makes the gradient 0. One more activation is left, Softmax. Softmax is a generalization of sigmoid, but we leave it to the end. Now comes the second component of NN learning, loss functions. Activation functions are used for calculating the NN output. Then we need to compare this output to the ground truth. We are at the comparison part. Each loss function here compares two vectors and returns a scalar value. First loss function is mean squared error loss. As the name suggests, we square the difference between two values, then take an average. Let's get started and make an Kerosene NumPy imports. Once again, the calculation for MSE, div, take the square and average over the dimensions. I import MSE from Keras losses. Let's examine the type. It's the loss function as we expect. I created two NumPy arrays. First, we will calculate the loss by hand. Here is the diff. Diff is element by element. Here it is. Then comes the square. Square is a vector too. Here it is. We sum up the three elements and then divide it by 3. So it's 5 divided by 3, 166. Keras MSE result is here too. We just feed the two inputs and get the scalar 1.66. What does this loss function do? Obviously, we want to compare some real valued vectors by summing up the diff squares. This makes sense if the vector elements represent some real numbers and we would like these two vectors to come close in the space. This calculation doesn't make sense if the vectors denote something else, such as probabilities or some categories. Let's make another computation of MSE. This time input shape is 2 and there are 3 batches. There are 3 points of dimension 2 in each vector that we want to compare. First, we ask Keras, value 7. Let's do it by hand. We diff the two vectors. We square the diff, like this. And finally, we get a mean per row. This losses per batch, I sum these 3 losses and divide it by 3. Final result is 7. It matches to the Keras computation. Where is it again? Here it is. Because in Keras, most of the computations involving batch is done per batch. And after computing the loss value per batch, we get an average over all batches. Now we will see MSE on action with Keras dense layer. Once again, this is the input and target I created for the first video. We will do a simple regression problem. Here is the input and output again, 20 points each. I will reshape the input and target. I will make them 20 to 1. Let's see it. How do they look like? So, input dimension will be 1 and there will be 20 such one-dimensional points. So each point in the space will be one training example and there are 20 of them. Hence, there are 20 batches. I will generate an output of dimension 1, 2. Then, this is the dense layer for this problem. Input dimension is 1, output dimension is 1. Okay, let's feed the input to the dense layer and call the result Y prediction. Here it is, 20 to 1. Then we ask the MSE between the target Y and Y pred. It is 9.35. The computation for Keras MSE is this expression. We imported MSE from Keras losses above. We feed the two vectors we want to compare. Can we compute with n? Yes, of course. I will diff the two vectors. Again, here it is. Then square the difference vector. Then I will get an average per batch. Here, please take care. I get the mean over axis 1. So I get a mean per row, which means per batch. Once again, I took the mean axis minus 1 because I computed an average per row and there are 20 rows in the input matrix. In order to get a final scalar, I averaged the loss over 20 batches. Here is the result. Great, as you see, this loss is perfect for regression problems where you fit the curves. So distance is the distance between points in 2D or 3D or more dimensions. What happens in binary classification? MSE is not very suitable for probability distributions. We need another loss function. That function is called binary cross entropy. Let's jump on to the next section. We will start with an example. Let's say we are doing a binary classification problem. We will have inputs like this, some points, and outputs like this, some labels. Basically, given some points, we want to just label them with a class label. So we want to sort them into two, either class 1 or class 0, or class A or class B. Labels are either 0 or 1. In Keras computations, 0 means negative and 1 means positive. 0, 1 can mean many things indeed. Positive, negative, dog, cat, female, male, chair, table, and so on. We want to label our points as either 0 or 1, this or that. Even if the labels come in other names such as cat, dog, we map them to 0, 1 before we feed them to the network. Hence, our network should output a single value, either 0 or 1. We already know that networks can output float points instead of 0 or 1 sharp. What if we output a number between 0 and 1? Then if the number is close enough to 0, it can be 0. Otherwise, we can round it to 1. Another view is that we can see the final output as a class probability of belonging to the class 1. How can we output a number between 0 and 1? Answer is easy, we already learned sigmoid. Let's do a tiny example. I will use this input and run it through dense with sigmoid activation. Here it is. We get 0.95, okay, sort of close to 1. How about this one? It's a similar number. This is a good estimation. This is a good estimation too, close enough to 1. But by some training and iterating, NN can make it really 1. Okay, now comes the loss. I will import the BCE from Keras losses, create a loss object, then compare these probabilities. These two probabilities I pick. I will compare 1 to 0.26. Let's see the number. Here it is, 1.34. Also notice the shape, how I fit the probabilities. I fit them as the batches of 1. Here is the result again. 1.34 is a scalar. We are ready to see the formula to understand how this value is calculated. Let's see the formula. Here it is. It reads as y, the true label, compared to the p, the predicted probability. The BCE between them is calculated is as follows: y log p plus 1 minus 1 log 1 minus p, and a minus in front. Let's make some calculations to understand how this loss behaves. I made a table of predicted values from 0 to 1 to show how BCE changes. Also, we can plug in the values and do the calculations. Okay, let's start. I will plug in 1 for y, 0 for p. Here is this. Here is the calculation. Here I put 1 for y, and I will put p for 0. So this is 1 times logarithm 0. Logarithm 0 is minus infinity. And this side dies because y is 1. This term is 0. Right hand side dies. So it is minus time minus infinity. It is just infinity. One more time, one more calculation. Between 1 and 0.26, 1 goes here. 0.26 goes here. So this is logarithm 0.26 here. This side dies again because y is 1, and don't forget the minus in front. It is minus minus this number, and then we get 1.34 as Keras computed. One more. Finally comes comparing 1 to 1 result, which is just 0 because values are identical. If you look at the values, you see descending loss values here. When the predicted probability comes near real probability, loss gets smaller and smaller. We quickly observe that if y is 1, this term dies because of 1 minus 1, and BCE becomes minus log p. If y is 0, then this term dies, and this term stays, and we don't forget the minus in front, hence it is this one. One quick question about infinity and 0, wouldn't they be bad for the derivatives? Surely they do, but sigmoid doesn't really output 0 or infinity, because they are asymptotes at that values, if you remember. So think of infinity as a very big number, 0 as a very, very small number. How someone invented this function? It looks very good, right? Entropy is a concept of probability and information theory. It measures how similar two probability distributions are. I left a link if you want to find out information theoretical explanations. This is great if we have two classes. What if we have more than two classes? We need a generalization of sigmoid and binary cross entropy. Here we welcome softmax and categorical cross entropy. So it is something like this. When we want to output only one probability, we output with sigmoids. But if we need more probabilities, we will output with softmax. Let's see this combo. We start with softmax. Once again for sigmoid, we took the NN outputs and squashed them to one float, which represents a probability. If there are four classes, we can output four numbers P1, P2, P3, P4. Each means probability of the instance belonging to classes 1, 2, 3, and 4. How can we achieve it? We can use softmax function. Softmax function is a function that turns a vector of floats to a vector of floats between 0 and 1 that sums up to 1. Input values can be positive, negative, 0, anything, but softmax transforms them into probabilities. Let's see the formula, do some computations, then come back to discussion. Here is the formula. Let's compute softmax of this vector. According to the formula, ith coordinate of the softmax vector should be e to the that element divided by the sum of exponents of all elements. As you see, nominators sum up to denominator because we normalize everything by the sum. Hence, these three numbers should sum up to 1. So the result is a probability distribution. Indeed, probability distribution for three potential labels. So let's do the computation. First, we will put the nominators e to the 0, here it is, e to the 3, and e to the 1. I calculated them here, and we will divide all of them by the summation. Here is the summation of these exponents. So once again, they should sum up to 1 because nominators sum up to denominator. Here is the softmax of this vector. We notice that the elements of the input vectors are scaled into numbers between 0 and 1. We also notice that ordering is the same. Biggest number of this array is 3, 1, then 0, transformed into 0.8, 0.11, and 0.04. Due to the exponential function, biggest number 3 dominated everyone else and generated a big weight. Think this vector again as a probability distribution. The winner is second label because it has the most weight. So class 2 is the output of this classification task. Then softmax looks like an argmax indeed, but in a softer way. If we take the argmax here, it's just index 2. Softmax instead returns floats but still points to the second element, so softmax is a softer, differentiable and smooth version of argmax, hence usable NNs. Remember, non-differentiable functions are no good for NNs. We look for smoothness in all activations. Let's see Keras on action. Here is a dense layer, takes a 5-dimensional input and output a vector of 3 probabilities for class 1, class 2 and class 3. Here it is. So basically what we do is that we take this vector of size 5 and then we generated a vector of size 3 outputting 3 probabilities for 3 potential classes. Now comes the question, how do we compare ground truth label to predicted probabilities? First of all, result is a vector of number of classes, but class label, so something like this, is just a number 0, 1 or 2, class 0, 1, 2, or something else, maybe blue, red and yellow. Remember that enants are not very friendly with counting numbers. It's better to have some floats as well. As a result, we can transform labels into some sparse arrays like this. We put a 1 to the position 0 to encode class label 0. Position 1 for class 1, position 2 for class 2, and so on. This is called one-hot encoding. If you make an argmax over these vectors, you turn back to the class label. We don't do it with hand. Usually NumPy and Keras has some util functions. I use to categorical of Keras utils. Here are some examples of one-hot encoding. We give the class label 3, here it is, and number of total classes should be 5. So we will put the 3 class label into the third position, 0, 1, 2, 3. Here it is. If we make an argmax over the result, we turn back to the original class label. If we pass an array, or just let's make one more example, here it is. Here our number of classes is 4, there are 4 positions. Class 1 goes to here, first position. And we can pass an array like this, then we get one-hot encoding of all array members. Here is 3, 3, 1, here is 3, 3, 1. Great, we prepared the class label, we outputted the vector of probabilities, and all we need is a loss function. There comes the categorical cross entropy. Here it is. Here is the formula. This formula reads as follows. For two probability arrays, where y is the ground truth again and p is the predicted labels, we just multiply the element yi to the logarithm of pi. For each position I, we multiply the ground truth probability with the log of predicted probability. Please carry the minus sign in front again. Okay, let's do computation for some ground truth and predicted label couples. Let's do it. So this one. Here it is. The correct label is just class 0, so I put a 1, 0, 0, 0. And prediction is class 1 by probability 0.9, class 2 by probability this, and class 3 by probability this. Okay, so it is 1 times logarithm 0, then all zeros, because this yi goes to 0 here, this allows zeros if I multiply by them, so this term is left, and hence we get this. And this is the way to call the Keras CCE function. Oops. Okay, I will just comment it out. Here it is. Result is the same. Let's change the predicted probes a bit. This time we will still predict the class 1 correctly, but we will give some more weights to class 2, like this. Here it is. Oopsie-doo. Result is the same because these positions are zeros. So these guys come as zeros to the total sum. Only this term, position, this position of 1 mattered. How about this input pair? Obviously, this is a... How about this input pair? Obviously, this is a wrong prediction. Real label is 1, but we put all the weight to the second class. This should bring a huge loss because this one will be multiplied with. So this one will bring 1 times logarithm 0, which is minus infinity. 1 more minus will be plus infinity. How about this input? Prediction is still wrong, but we distributed weights to class 2 and 4. Well, the result is not gonna change because these zeros will multiply. All will matter is the first position. There is one more loss function included in Keras losses called sparse categorical cross entropy. It's actually a shortcut. Instead of one-hot encoding your label, you can directly pass the class label as an integer. So like this. You import it like this, and then you give it like this. Prediction is still class probabilities because it comes from the Softmax, but this time, instead of one-hot encoding, you can just directly plug in your, class label. Please compare the inputs. Again, here we give the class label directly. No one-hot encoding. I usually use this function. That's it. These are the most basic and widely used activation and loss combos. Hope you enjoyed the video. Now it's your turn to play with some Keras code, I hope. Play a bit with regression, type problems, then jump to classification. After that, you will be ready for sequential input, and you may want to join my LSTM playlist. Until then, stay happy, safe and tuned. See you in the next videos, next playlist. Bye bye.